This is AB Calculus, section 1.1, day number 2, review of functions. Our objectives for today are to look at secant lines and the difference quotient, symmetry in graphs, which applies directly to this idea of even and odd functions. So secant lines and the difference quotient. A line through any 2 points on a curve is called a secant line. The slope of the secant line through those 2 points is given by the following. This notation here means slope, m meaning slope, sec meaning secant line. Change in y over change in x, which can be referred to as delta y and delta x. There are 2 main ways to express this. Here is the first expression for finding the secant line given 2 points. So let's take the point x, f of x, and we're going to call that point P. And we're going to take the point x plus h and f of x plus h. We're going to call that point Q. Okay, now the distance between x and x plus h, this length here in yellow, that length there is h. And the secant line visually would be this green line connecting P and Q. So the slope of the secant line naturally would be the change in y over the change in x. So the change in y is that length there between f of x plus h and f of x. So we would take y2, which is f of x plus h, minus y1, which is f of x, over x plus h minus x, which ends up being h. So the first form for this, or expression for the slope of a secant line, is the following. And this is referred to typically as the difference quotient. Difference quotient. Let's see if I can spell it right. Got it. Okay. This expression right here is typically referred to as the difference quotient. It is the slope of the secant line, and many times, as you can see here at the bottom, the slope of the secant line in this form is interpreted as the average rate of change. Okay, average rate of change over the interval x to x plus h. All right, let's continue on the next slide. Okay, let's look at the second expression. Just a different form, similar concept. We're going to call this point A and f of A. And this would be x, f of x. We're going to call this first point P like we did before, and Q. So this distance right here is no longer h. It's going to be considered x minus a. And this distance right here, of course, will be our change in y, or f of x minus f of a. Therefore, the second form for the slope of a secant line is also referred to, here's the secant line, the slope of that blue line would be f of x minus f of a over x minus a. So just a different form for the same topic or concept. Okay, so let's look at that concept of the slope of the secant line in example 1. Excuse me. So here I have f of x, which is x squared. I've got an interval from 2 to 3, which would be from a to x. So the slope of the secant line of f of x from 2 to 3 would be f of 3 minus f of 2 over 3 minus 2. So we're going to use f of x, which is x squared, to find that f of 3 is 9, and f of 2 is 4, and 3 minus 2 is 1. So the slope of the secant line on f of x from 2 to 3 is 5. So what would that look like? Well, f of x is x squared, and from 2 to 3, if we go from 4, an output of 4, up to an output of 9, the slope of this secant line is 5. Okay, let's continue on. All right, example number 2 is going to involve a lot of algebra. So let's start with the difference quotient. This is the first form of the difference quotient for the function f of x equals x squared. So f of x plus h, let's talk about these items, and then we'll build the difference quotient from there. Well, f of x we know is x squared. F of x plus h is x plus h quantity squared, which is equivalent to x squared plus 2xh plus h squared. So f of x plus h minus f of x all over h for the function x squared would be x squared plus 2xh plus h squared minus f of x, which is x squared, all over h. All right, as you'll see, we'll get some terms that when we combine them, they reduce. And I'm left with 2xh plus h squared over h. I'm going to factor out an h in the process, leaving this as 2x plus h all over h, which reduces out to 2x plus h. Okay, so I saw the h reduce, and therefore the difference quotient, or the slope of any secant line on f of x given x and x plus h, would be 2x plus h. So it's a very simple formula to look for. So the slope, or to work with, the slope of the secant line with f of x being x squared can be found using 2x plus h. So as I look at example 3, let me zoom out here. I think I'm missing part of it. Oh, there we go. Find the slope of the secant line for f of x equals x squared over the interval from 2 to 3. Okay, so that should be the same as example 1's answer. And we found the slope of the secant line for example 1 using the different form to be 5. Let's see if it comes out to be the same. So this is x and x plus h. So x is 2 and x plus h is 3. Therefore, if x equals 2 and h equals 1, then the slope of the secant line would be 2 times x, which is 2, plus 1, which would be 5. And look at that, we get the exact same slope. So the two forms for the difference quotient give us the exact same answer. Okay, let's look at example 4. Example 4 wants us to, again, we're going to use a lot of algebra here, but simplify the difference quotient in form number 2, right? F of x minus f of a over x minus a. So f of x we're given, what would f of a be? That would be a squared plus 1. Okay, so we're going to build this using f of x and f of a and x minus a. So that will be f of x, which is x squared plus 1, minus f of a, which is a squared plus 1, over x minus a. Now, the way that we'd simplify something like this, anytime you see radicals, we're going to multiply by what's called the conjugate. And the conjugate is the same as the term which it is a conjugate of, except we change the sign in between. So instead of square root of x squared plus 1 minus square root of a squared plus 1, like this, its conjugate is the same term with the opposite sign in between. So I got to multiply top and bottom, numerator, denominator, by the same thing. Square root of x squared plus 1 plus square root of a squared plus 1. Now the great thing about conjugates is when you multiply, all right, so when I'm multiplying out the numerator here, I don't have to do too much work, because when you multiply conjugates, what you'll see happens is these two, square root of x squared plus 1 times itself just becomes x squared plus 1. The outside-inside terms, because of the signs being opposite, so I'd get outside and inside, well, they'd be the same term except opposite signs, so they would reduce. So foiling conjugates actually becomes just first last. So it's kind of nice. Okay, and then when I multiply square root of a squared plus 1 times a squared plus 1, I get this. Okay, and now the denominator is going to be messy. but we can do some work with that. All right, let's go x squared plus 1 plus square root a squared plus 1. Hopefully you're sticking with me here. Now look what happens in the numerator. All right, so I see the 1's reduce out, and I get x squared minus a squared, which is factorable. So I get x minus a times x plus a in the numerator, which you'll see will reduce nicely in the next step. Square root x squared plus 1 plus square root a squared plus 1. So the difference quotient is going to reduce or simplify to x plus a over the quantity square root of x squared plus 1 plus the square root of a squared plus 1. And there you have it. That is the simplified difference quotient. Oops, that should be an a over x minus a. Here you have it. Now, we're going to revisit that a lot later on in further chapters, so this is a good skill to be competent in. All right, so let's talk about even and odd functions. So here I've sketched out 3 even functions. Okay, this is even because it has symmetric properties with respect to the y-axis. So if I reflected the function over the y-axis, the points would match up. So in this case, the outputs for 2 and -2 are exactly the same. Okay, and then you've also got y equals cosine x, same properties, and y equals 1 over x squared, same properties. So if a function is even, then f of negative x is equal to f of x, which just means that inputs of, say, -2 and +2 would say have the same outputs. In a similar manner, odd functions, like the functions given here, y equals 1 over x, y equals sine x, and y equals x cubed minus 4x, they have the property that the outputs for opposite inputs, so for 1 and for -1, have opposite outputs, right? So let's say y of 1. Well, y of 1 is 1 over 1, whereas y of -1 is equal to -1. Therefore, a function is odd if f of negative x is equal to the opposite of f of x. That is the property that makes a function odd. So I've got an odd property and an even property of functions. Now some functions are neither, right? Neither even nor odd. We can see it either geometrically on a graph or algebraically. So let's look at how to algebraically show that a function is even, odd, or neither. Take example 5. Okay, if a function is, remember, even, then f of negative x is equivalent to f of x. If a function is odd, then f of negative x is equal to negative f of x. So what we're going to want to do is figure out what f of negative x simplifies out to be. So let's take f of x and plug in a negative x. All right, so by rules of exponents, a negative value to an even power will make that x to the 4th, which is equivalent to f of x. Therefore, f of negative x is equal to f of x. Thus, f of x is an even function. Okay, let's continue. Example 6, a little bit more complex example. We're going to plug in a negative x. So I get negative x to the 3rd power over negative x to the 2nd power minus 1. So the numerator will simplify to negative x cubed. The denominator will simplify to x squared minus 1. You can see that that's the same denominator as f of x. Now this is not equal to, here we can see that f of negative x is not equal to f of x. Therefore, we could say just mentally, this is not an even function. So my next logical step would be to pull out a -1. And if I pull out a -1, I would have x cubed over x squared minus 1, which if we look on the inside of the parentheses, we'll notice we see f of x. So this is the same as negative f of x. So we have shown algebraically that f of negative x is equal to negative f of x. Therefore, f of x, is even, or excuse me, is odd. Okay, let's continue. All right, example 7. We've done an even, we've done an odd. Let's see if we get a neither here. We're going to plug in a negative x into each of the inputs of f of x. We're going to evaluate or simplify. Negative x to the third is negative x cubed, but minus a negative x cubed is plus x cubed plus 2. Notice that right here I know that this is not true. So we know mentally that the function is not even. Okay, I'm going to pull out a negative 1. And you might already notice that the inner function is not going to end up being f of x. Therefore, I see that f of negative x is not equal to negative f of x. Therefore, okay, I could just kind of leave f of negative x as any of those, either of those two equations, and we would say, therefore, since f of negative x is not equal to f of x, and f of negative x is not equal to negative f of x, f of x is neither even or odd, nor odd. Okay, now it is very important that you show all the algebraic steps and you give a nice justification at the end for full credit in both this class and on the AP exam. Okay, so let's look at the last two examples here, and then we'll wrap up the video for today. Assume f is even and that g is odd. Okay. Example 8 says find g of f of negative 2. Well, the first thing that I'm going to do is if f is even, then f of negative 2 is going to be equal to f of 2. All right, if it's even, that would have to be true. So f of negative 2 will equal f of 2, which is 3. So g of f of negative 2 would be equivalent to g of 3. And g of 3 is given, right? G of 3 is given here. G of 3 ends up being 4. Since g of 3 equals 4, then g of f of negative 2 is equal to 4. Okay, one concept that I did not talk about when looking at these origin symmetry or odd functions, right, that have symmetry about the origin, is that if g of x is odd and g of 0 exists, then g of 0 has to equal 0, right? So in the functions that I showed you, I think I showed you 1 over x, right? Well, g of 0 doesn't exist in 1 over x, right? So y of 0 doesn't exist. Y of 0 does not exist. But then the second function I showed you was sine x, right? So y equals sine x. Well, y of 0 equals 0. And then the third example I showed you was cubic polynomial, and that also, right, I think it was y equals x to the third minus 4x or something like that. If y of 0 exists, it must equal 0 with an odd function. All right, if it doesn't exist, then g of 0 doesn't exist. So I'm going to assume, based on this problem, that g of 0 exists. Therefore, g of 0 equals 0. And g of 0 plus 2 would then equal 0 plus 2. Thus, this would be equivalent to f of 2. And f of 2, based on the table given above, is 3. Therefore, f of g of 0 plus 2 would equal 3. Okay, guys, that is it for 1.1 day number 2. See you in the next video.